What's up everyone, welcome back to a new video. So with this video I want to start in sort of a little series about a little theory and practice in how a vacuum tube Tesla coil works and how to tune a vacuum tube Tesla coil. So because I got many questions from you guys in my last few videos, how about to do this? What I'm doing to tune my Tesla coil, how I got there. So as you've seen in my last videos, this Tesla coil gets bigger and bigger and bigger and more powerful. Yeah, and now I think I reached a point where I don't know everything about it, about this topic, especially not about the theory, but I think I worked it out pretty good to represent some datas to you guys that might be helpful for you. So, and yeah, this is the first video about this little series I want to make. And yeah, I would say we start just with the basics, and yeah, and I want to keep it really simple in this area. So I just want to scratch the surface and want to show you how the basic oscillator, in my case an Art of Armstrong oscillator, works. And yeah, and then we move on to more precise things that will happen in this Tesla coil, in this oscillator. And yeah, I will do more videos about this because this thematic is really big, really complex, and there are many things in there that I want to talk about and want to show you. You might have some questions about it, and I have some questions about it too, to you guys, because like I said, in some points I'm actually not really sure how they work, so I just worked it out by just trial and error. So I think I will have one or two questions to you guys. Someone might be knowledgeable enough to answer this, but yeah, I would say let's start it. So just for the rough basics here, so I really want to scratch the surface here just to understand a little bit how this oscillator will work. So this can be really helpful just for understanding what we're doing here on our Tesla coil. I just draw a little schematic, and yeah, how this all starts. The grid of the tube is just on the same potential as the cathode. So in this case, this tube can conduct some current, not really much, but this will conduct current in this state. So in this case, when we apply a positive voltage here, some negative charged electrons will flow through the grid to the anode. So this ends up in a current flow through the primary coil. Because of the current flow, the primary coil will build up an electromagnetic field, and because of this electromagnetic field we induce a little current into our feedback coil. This is really near the primary coil, so we come later to this, maybe in the next video. So because of this current we induced here, we charge, in this case because we wired the feedback coil 180 degree out of phase to the primary. So in this case, this grid will get really strong negatively charged. So in this case, the tube just shuts off, no current can flow. the rest of the electromagnetic field will break down back into the primary coil and induce a current in this coil, but in 180 degree turn. So this capacitor gets charged, maybe here positive and here negative. So when no stored energy in the field is left and the capacitor is charged, this capacitor will discharge into this primary coil. So in this case we build up back an electromagnetic field, but 180 degree turned to before. This induced an 180 degree turned current into our feedback coil. So in this case we charging our grid positive. Because of this, the tube will conduct really heavily and really big current can flow, and because of this big current flow we build up again a really strong electromagnetic field. This induces 180 degree turned again signal into the feedback coil. This shuts off the tube again, and yeah, this electromagnetic field will break down again into the primary coil and charge up the capacitor, and the whole cycle will return. So this is meant as an oscillator. So you can say in theory the oscillator of the Tesla coil, so this oscillator will work just without the secondary coil. So in theory I can remove the secondary coil from a Tesla coil and this oscillator will work just normal, like it work every time. There are some other problems that will came with that, but yeah, just in theory. So much to just a really rough understanding how this oscillator will work. So the frequency of this oscillator now is depending on two things: of the capacity of the capacitor, of the primary capacitor, and of the inductivity or reactance, or we can just say the resistance of the primary coil. So when we have a big capacitor, or I just say we have a 1.2 nanofarad capacitor, this will have, or this will need some time to discharge into the coil to get rid of all its inert energy. And when we get a little bit bigger capacitor, this will need just a little bit more time to discharge into the coil and build up the electromagnetic field. When we use a little bit smaller capacitor, this will discharge really much faster into this primary coil. Or when we stay just with this capacitor like it is and we use more turns, the resistance of the primary coil will be bigger and the capacitor will need more time to discharge through this coil and store all its energy into the electromagnetic field. Or when we change this to way less turns, the resistance of the primary coil will get less and the capacitor can discharge really fast into this coil, get rid of all its energy really fast and build up really fast an electromagnetic field. So we can tune this. This is known as an LC circuit. So C stands for capacitor, L is for an inductor or for the coil. So we can tune this LC resonance frequency depending on how big we using the capacitor or how many turns we using, or how thick the wire is that we're using on the turns of the inductor, or how we, yeah, how should I say, how wide the gaps between all the turns of the inductor. So when we space the turns much wider from each other, the inductance gets less, and the real resistance of this coil, or we know it as reactance of this coil, will be less. So the resistance will be less, and the resonance frequency of this coil will be a little bit faster. So there are many factors that they play this game. So this LC circuit alone is really complex when we work with this in the practice. So when we just build a Tesla coil to tune the circuit, there are many things we can change to not only change the resonance frequency. So there are many other things, the coupling to the secondary coil, or the height of the primary coil to the secondary coil, because we want a really high coupling. So to get to this now. So when we think about the power transfer from the electromagnetic field into the secondary coil, we want we don't want many losses about this. So we want to have this primary coil really near the secondary coil and have a really strong electromagnetic field to induce as much power as we can with this air core transformer, because we have no metal core or something like this. So we have to get really close with the coils each other. But when we get too close, we get an arcing from the secondary to the primary, or the other way. So somehow we have to try to build a coil or an LC circuit that has the right resonant frequency to the secondary coil and has the best coupling we can get with that to get the best energy transfer to this coil, but also don't get too strong with the coupling or too near with these both coils, because we don't want to arc between the coils, because this will end probably really bad for the tube because of high current or voltage spikes that go somewhere. We don't want this. So in this case we have to find there a good way. Also, we have to be careful with the tube, because the tube don't like low impedances, because this is a high impedance device. I said so. The tube can switch just it can switch really much current. So we have to be really careful with that, because when we load the tube really hard down to stress this to switch really high currents, this anode will begin to glow and overheat, and the tube will melt down. So in this case we have to get the right load for the tube. So we need a high impedance load, but not too high impedance, because we will have really high current flows in this LC circuit. We want to have a really high coupling to the secondary coil, but not too high because of arcing between the both coils. We want to have the right resonance frequency to match these coils and resonance frequency. There are many factors. So that's because that's why this just really simple oscillator gets really fast, really complex. So all this we can calculate. So just because it's not even complex enough, we have a second LC circuit. So the second LC circuit, or resonating circuit, that has its own resonance frequency, that's the secondary coil. So in this case we have just a sort of the same schematic like this here with the secondary. Just the secondary has really many turns, and this capacitor is the top load. And when we think about capacitor is one plate and an dielectricum, and the other plate for the other pole, we have here the top load as a plate. Then we have the air as a dielectricum, and we have the earth, or the ground potential, for the other plate. So in this case we just have an LC circuit here too. Problem with this LC circuit is that this has not a fixed resonant frequency. So when we look at this LC circuit, this just has one resonant frequency and all is fine. So when we just calculated this out or tried this out, however we done it, it has its own resonant frequency, and it stays, in theory, it stays really much the same like it is. So, but in this case, because we're using the air as a dielectricum, so this capacitor will varying its capacitance a little bit, and this is depending on how the humidity is on the air, how the air pressure is, how the air temperature is, or yeah, the air temperature is, or the pressure is depending on the temperature. But yeah, not only. Oops. There are many factors playing into this, and also we are producing arcs here, and these arcs are just channels of ionized air that are really conductive. So these are, I can say these are, yeah, like an part of the top load or one plate of the capacitor. So when we have a big arc, it creates a little bit bigger top load in this case, and the capacitance gets a little bit bigger. Yeah, or the capacitor gets a little bit bigger in this case. So because the capacitor gets bigger with a bigger arc, the resonance frequency of this coil gets lower, because this capacitor needs a while to discharge. And it needs a little bit longer to discharge when it has a bigger capacity. So in this case, the resonance frequency is changing over the time, even with different air conditions, or with arcs that getting bigger or smaller over the time. So this is a problem, because when we calculate just these resonators in its theory, we calculate this as 400 kilohertz, and we calculate this at about 400 kilohertz too. We have the problem when there are really long sparks or arcs getting out of the top load. This loads down the coil more because of the high capacity, and we end up somewhere at I just saying 360 kilohertz. And now, with a bigger arc, the system is falling out of tune. So the energy transfer between these both coils is not ideal, because one resonator is falling out of tune. So we can compensate for this. Let's say we just tune this primary circuit to 360 kilohertz, because we somehow know how on what resonant frequency the secondary coil will end up. We tune this primary coil a little bit lower to 360 kilohertz. This system will start out of tune, but it's not bad. Just the energy transfer is a little bit worse, but it will just start up fine. So some arcs will break out the top load and will getting or make bigger the capacitor, will load down the system more and more. And yeah, when the arcs getting bigger and bigger and bigger, this whole system will fall more and more in resonance, and the energy transfer between these coils will getting better and better until it's reaching its ideal or best resonance frequency. And yeah, that's something we have to get in mind. So there we have the first data. Something that I find out and something that I have read many times on the internet is that when we just roughly calculate the resonance frequency of the secondary coil, we can calculate then how we getting the primary coil to the right resonance frequency to the secondary coil. And then we just say, yeah, let's just use 10% bigger capacitor as calculated, because we know later when some arcs are there, the resonance frequency of the secondary will drop down, and then the system gets into resonance. So I hope you get the point. It's really not easy for me to describe this on English, but I try my best. Please don't rip me apart in the comment section. But when you have something to say, please say it. But be kind with me, please. I try my best. Try my best here. So much for this. I would say this is the rough understanding of the system. And yeah, we came here to one point. I think you wonder, hey, you forgot this. This is one thing I want to question you guys, because yes, I know the resistor, or even when someone uses a lamp, a tungsten lamp, yeah, this is limiting the current or the overall power that's dissipated on the grids, to save the grids to not to melt down, and a little bit to being able to regulate a little bit the power, how heavily this tube will get switched. But what I wonder, I read many different things about this capacitor. So that's something that I wonder. I read so many things from yeah, how should I say this on English, to correct the phase on the feedback, or on correct some timing on the feedback. So I read many different things, and I was experimenting by myself with this coil with different capacitors on it, and yeah, it does not do much, but it does some things. So, and I wonder what exactly these capacitors are for. Yeah, like I said, I read many things, and yeah, these are all plausible and yeah, make sense, but I'm still not that sure when I'm honest. Yeah, that's one of the points. When someone of you really know exactly what this RC circuit does, yeah, please write this down in the comments. That would be really interesting for me. Yeah. So I would say that's it from me today. I hope I can help you out a little bit with this video to understand this oscillator circuit a little bit better. And I hope I get the things right. So I know there are many more things, many more details that plays into this, and I just want to scratch the surface, like I said, and I just want to tell it how I understand it and how I manage to understand this. And yeah, when you have questions about this or when you have ideas how I can do this a little bit better, or when I just forgot something that's really yeah, that you want to know, or or even when I done something wrong, so yeah, please correct me in the comments. But yeah, I hopefully got it right. So yeah, that's it. That's the basics for today. With the next video, I will go more into tuning and I think more how to build the primary coil and how to tune the feedback. So this will be, yeah, really complex too. But I will try my best. So have a nice day, have a nice evening, have a nice morning, whatever. Bye bye.